Thank you for the kind introduction and also for the invitation to come speak at this workshop and have some very tremendous conversations with a lot of scientists in this field. It's a very heterogeneous field and there are a lot of challenges, and I think that together we can really figure out some solutions to these problems. So today I'm going to be talking about single entity electrochemistry, and as an outline I'll tell you what an entity is, what is measurement science, why study single entities, examples, and the story of single atoms that Professor Faulkner alluded to yesterday. And I'll talk about frontiers and final thoughts that I put together over the past couple days watching. I've had the benefit of watching a lot of talks before me, so I could edit this as I went on. So what is an entity? So you are an entity. Entity, I just mean one thing at a time. Entities go from very large entities, Earth is also an entity, all the way down to single atoms. And you have things in between like the bane of my existence, ragweed pollen. And you have nanoparticles and DNA strands all the way down to single atoms. These are entities. And now you can detect a lot of entities electrochemically. A lot of us have all had microelectrode experiments in our laboratories that weren't well grounded, and when someone walks by, you detect a person. So you can't observe a single person walking by on an ultramicroelectrode. What is measurement science? So my colleague at UNC, Royce Murray, when he was editor of Analytical Chemistry, says that measurement science is measuring important chemical things. And I love that, and I love its simplicity. So that's measurement science. And so now why... That's it. That was all for that slide. I'm not going to read this to you. So why study single entities? So we saw a talk earlier where you saw a variety of faces, and then you saw the average ensemble of all of those faces. And obviously, it was sort of creepy to look at that average ensemble of all these different faces, but it didn't really represent the detail of all the individual pictures. I'm going to give you a little bit of a different metaphor, and I hope you can stay with me through it. I hope most of us here have seen fireflies, right? Most of us have, yes? So I want you to imagine you've never seen a firefly or you've never heard of a firefly before, and your colleague asks a favor. She places varying amounts of fireflies into 3 large jars. I want you to think of a jar that looks like this, but on the size scale of the world's largest whiskey bottle. I think that this was in the Czech Republic. Really big jar, so you can pump in a lot of fireflies to those jars. And she asks you to come to some general conclusion about the light generated by a firefly. So being a very good measurement scientist, you write some notes in your lab notebook and you take some pictures, and you find that the intensity doesn't really vary a lot with time, and the intensity scales linearly with the number of bugs in the jars. And so you might come to the conclusion from these observations that fireflies continuously bioluminesce. And that's not true. We all know that's not true. Misconceptions of nature arise when careful measurements are not taken on single entities. Not until scientists like W. Murner started studying the fluorescence of single proteins did we know that the fluorescence can blink off into a metastable dark state. Murner further used this blinking phenomenon to develop his taste of super-resolution microscopy, for which he shared the 2014 Nobel Prize in Chemistry with Eric Betzig and Stefan Hell. And as an analytical chemist, there are 2 exciting ramifications of these experiments. I'm also a physical chemist as well. So the first is more physical. We can now develop techniques to study the chemical and physical properties of single entities, which I hope I've convinced you can be vastly different from just looking at ensemble amounts. Think back to the firefly or to fluorescent proteins. Second, it takes measurement science toward a digital era. By digital, I mean 1-0. It's there or it's not, where the limit of detection is one entity, one molecule, one atom, one nanoparticle, one circulating tumor cell. And so in 1995, Al Bard and Mark Whiteman, Shelley showed a picture of Mark Whiteman earlier. That was when he still had the mustache. This is Mark without a mustache. It's a more recent photo. published papers almost back to back in Science. Al's paper was on looking at redox cycling in nanochannels of single molecules, and you can amplify the Faradaic signal of a single molecule. And Mark was looking at single chemical reactions in solution by looking at electrode-generated chemiluminescence and watching photons come out and hit a photomultiplier tube. About 10 years later, I think, in 2004, Serge Lemay published a paper in JACS where he was observing latex microspheres colliding with ultramicroelectrodes. There's a historical reason why we call it ultramicroelectrode. I won't get into that, so I'll just call them UMEs from here on out. So UMEs are below a radius of about 20 micrometers or so. And so the basic idea in Serge's paper was this. You have a well-grounded Faraday cage, and you're doing your experiment in your Faraday cage because when your colleagues walk by, you do not want to detect them and the noise. You drive a reaction at the electrode surface, and when something comes up to the electrode by Brownian motion, hits and irreversibly absorbs to the electrode, it will decrease the signal. This is just an area decrease. And it's manifested in just a decrease in current if you're measuring the current as a function of time. That was 2004. 3 years later, Bard and Shao published this paper on electrocatalytic amplification, which I'll get into the details a little later on. And really after that, this field has just blossomed. Folks have found lots of different ways of measuring single entities one at a time for different types of entities, whether they're insulating, like this, what I just talked about earlier, or if they're electrocatalytic, say the metal like copper or silver can dissolve under a certain bias. You can detect single nanoparticles that way. You can use water or oil nanodroplets and load redox materials in those droplets, and you can do electrochemistry in sub-femto to attoliter. That's 10 to the minus 15 to 10 to the minus 18 liters. And you can get some really exciting results. And one thing that I'll talk about also, if you can make these collisions specific to a colliding entity, that's when you have reached a limit of detection of 1. So Serge's paper it's called blocking, where you block a certain area of the electrode surface, basically works by driving a reaction. You measure a current. As the entity comes in and begins perturbing this diffusion layer around the microelectrode or UME surface, then you start to see this decrease in current. It's not an increase. I'm drawing it in the Texas Convention or Hurofsky Convention, what have you. It is going towards 0 here. We've been able to take this all the way down to single molecules, large biomolecules, looking at those colliding with nanoelectrodes. We've been able to use virus particles and use an enzyme to, a glucose oxidase enzyme appended to a primary antibody specific to a glycoprotein on that virus surface. And we're able to see this ferrocenium type of catalytic enhancement when a virus that is surrounded by glucose oxidase approaches an electrode surface. There are a few techniques that have made collisions specific. This is one of them. And we were able to pick out viruses in the urine of infected mice. I do want to make a very strong point in that I think in this field moving forward, it behooves all the scientists who work in this field to correlate collisions with microscopy. These experiments are not incredibly difficult if resources are available, and it really enlightens what you're seeing in the electrochemical response. Whether or not it's one entity moving around, that happens. Whether or not it's coming on and coming off, that also happens. So correlations with optical microscopy and eventually atomic force microscopy, etc., are really important for this field moving forward. So I'm going to talk more about electrocatalytic amplification. This was a very nice paper published in 2007 from Al Bard's lab. This was about 6 years before I started there as a PhD student. And the basic idea is this. I have reactions, inner sphere reactions, where the heterogeneous kinetics of those reactions depend on the electrode material. So I can have a reaction like proton reduction. Proton reduction goes at a very slow rate on carbon ultramicroelectrodes, carbon UMEs. But proton reduction, as we all know, is super fast on platinum. And so if I hold a potential, so this is proton reduction on carbon, almost non-existent in this potential window. Here's proton reduction on platinum. There's a huge amplification, hence electrocatalytic amplification. That's what this technique is termed. Now, if I bias a carbon microelectrode at a potential where proton reduction occurs on carbon, but not on, occurs on platinum, but not on carbon, then a platinum nanoparticle is incident on the electrode surface, I get a brilliant amplification. Single nanoparticle amplification. Yes, it decays. People have been looking into this decay. There are theories about this decay. But this was in the first paper. So I can get reactivity of single nanoparticles one at a time. So here's a fun question that Al actually came to my desk in 2014 and asked me. How small of a nanoparticle can we observe? And so I started thinking about this, and if you look at the number of atoms that make up certain size nanoparticles, and you have an equation for current, and you can calculate with, if I want to electrocatalyze, again, proton reduction on platinum, and I say, what is the current that I get for a platinum atom, which has a radius of hundreds of picometers? It turns out to be greater than 10 picoamperes. The signal to noise in a well-grounded Faraday cage is on the order of hundreds of femtoamperes if you get really good at working with noise. And so signal to noise, you should be able to see this. You should be able to see a single atom. And I did this calculation and aha, it's those few aha moments that we have in science. And then of course you go in the literature and you find that people have predicted this before. So in 1994, Stan Pons and Martin Fleischmann published a paper on the electrodeposition, electrocatalysis, the dissolution of single catalyst centers. Of course, this was after cold fusion. This paper is not incredibly highly cited, but they do say that it is shown that it should be possible to detect catalytic reactions in a single atom of the new phase. It does say that's the last thing it says in the abstract. They deal with it at the end. How do they show it? They show it basically by the argument that I show you here. So 1994. Correct. It's after. Yes, correct. And so here's the experiment we devised. If I want to get single atoms onto a rather inert surface, I need to control the rate at which those atoms come down to the surface. Now, it's very hard to control that rate by controlling the current because I'd need an incredibly low current. So instead, I control it by mass transfer, where I have femtomolar chloroplatinate. We have femtomolar chloroplatinate for hundreds of nanometer microelectrode, ultramicroelectrode. The collision rate of one molecule is roughly 1 every 10 seconds or so. And so every 10 or so seconds here during my plating time, I can get one atom. I can then exchange out the solution to a solution where I can do electrocatalytic amplification and hopefully see the voltammetric response of single atoms. And so this is the thought experiment. This is how it looks in practice. So I do the electrodeposition and femtomolar chloroplatinate for 10 seconds. I take it out. Sometimes I get nothing. Sometimes I get this type of curve. Sometimes I get this type of curve, and more and more rarely do I see higher currents. And now with these currents, I can calculate the size of the platinum deposit that has been put on the electrode surface. And when we do that, we get about 0.25 nanometers. This is roughly the 250 picometers I was talking about before. And as all of you may know, some of you may not know, the collisions of these chloroplatinate molecules one at a time follows a stochastic process. And so if I have a 10-second deposition time, 37% of the time I get one atom, 37% of the time I get nothing, and then it drops off from there, 2, 3, 4, and 5. And you can see these Poisson distributions for, I think this was a 10-second deposition, and this was a 20-second deposition. And the experimental count amounts that we get seem to follow the Poisson distribution quite well for this extremely difficult experiment. If you do the general collision experiment tracking the amperometric IT curve as of just current as a function of time and driving an electrocatalytic reaction, proton reduction for, say, for platinum or chloroplatinate. How about methanol oxidation for PbO2? We can do proton reduction for nickel. We see collision types of responses. The important point here is we can make calibration curves for trace metals in the femtomolar parts per quadrillion regime. This is incredibly sensitive. It's at an area that I don't think a lot of analytical science is at in terms of these detection limits. Of course, these were ultra-pure solutions, as admittedly they were, but proof of concept, we're down there. So many of these experiments require nanoelectrodes to enhance the sensitivity. So there are many different ways of making nanoelectrodes. The first way, one of the more popular ways, is by laser pulling the nanoelectrodes. Now, if you put a platinum wire into a capillary, you heat that capillary with a CO2 laser, and then you pull it very quickly. It pulls into this very, very sharp tip. But we can also imagine different ways and get clever about how we interpret nanoelectrode electrochemistry to get at some of these reactivities. We were talking about before having to integrate over hundreds to thousands of nanoparticles to get really good information. And what I'm interested in is how the electrocatalysis, as you saw back here, for single atoms may differ from a larger cluster. This is a cluster growing. Not only does the limiting current increase, i.e. the size of the cluster, the half-wave potential changes as well. This is a kinetic effect. So we're also interested in studying how kinetics might change as a function of cluster size for these inner sphere reactions. Sorry I didn't make that point earlier. So let's get clever on how we make nanoelectrodes. Scanning electrochemical cell microscopy is also another way to make nanoelectrodes. In this sense, you have a meniscus in a dual barrel pulled capillary. You come down to a surface, and wherever you touch the surface and scoot along the surface is effectively a nanoelectrode. Another thing that what my group has been working on at Carolina is using water nanodroplets and putting in chloroplatinate or other metal salts into water nanodroplets. We can get very nice nanoparticles, mass transfers fast, so we can also get high entropy alloy nanoparticles. And the size of these water droplets is on the order of a micron in diameter. We can control the size, control the distribution by adding in surfactant. The important point here is the contact radius between the droplet and the electrode surface is on the order of tens to hundreds of nanometers, effectively a nanoelectrode where we can do nanoelectrochemistry. And we were able to do this with single cluster electrocatalysis. Back in my PhD, I was using femtomolar concentrations of chloroplatinate. Turns out if you have an attoliter volume, nanomolar concentrations are on the order of 1 to 10 molecules of chloroplatinate inside a single droplet. So we can look at these droplets colliding with a microelectrode. We can electrocatalyze water reduction. This is not very fun. Actually, it's a ton of fun, but this is not a very good system to study because when we're reducing the droplet itself, making it much more alkaline. And so what we did was we then fished out the clusters, and we were able to do voltammetry on the clusters and control their size very well just by controlling the droplet size. And so I have a few final thoughts that I want to leave you with in terms of where I hope that this field goes. I think that we have a ton of fun in lab making droplets and studying electrochemistry in droplets. You can trap a lot of things in droplets, and it's all nanoelectrochemistry, and you're doing it one at a time and studying reactivity one at a time. The major challenge moving forward is using these concepts that I've told you today and learning a new truth of nature, really learning something. I took that from Adam Heller, learning new truths of nature. He says that a lot. But I really think that if we move this field forward, we have to not only focus on observation of X on UME, observation of Y. No, we need to come up with some really good fundamental science with these experiments. So a few final thoughts. I think the elephant in the room is the inter-sphere reaction. Gaining a fundamental understanding of these reactions on the most basic level is important for all the applications we've talked about here over the past day and a half. Second, we have entered an era where the limit of detection is a single species, a single entity, an atom, a molecule, a nanoparticle. We're poised to learn new truths of nature one at a time by comparing these, and correlated measurements will enhance our understanding of what's going on with these different electrochemical processes. It's also an opportunity to make very sensitive sensors if you can make it specific and it works in a complex matrix. The resolution in electrochemistry is not limited by a fundamental limit, i.e. the diffraction limit of light for fluorescence measurements, but rather the smallest electrode one can make. And that is, in principle, a single atom. Now, how we take this atom and use it to image in situ, if we ever want to image the flux coming out of a membrane protein outside of a bacterium, we really need innovations to move this forward in terms of imaging resolution. And finally, this has nothing to do with my talk, but something that I said yesterday. I have a lot of passion for this. One can electrosynthesize many organic compounds. There's a beautiful book by Manny Baser. It's Organic Electrochemistry, an Introduction and Guide. Perhaps I missed it, but I didn't see it in any of the references for electrosynthesis. It's back in 1973. It's a really good book. Nobel Prizes have been won for creating bonds, but one can also break them with electrogenerated radicals. We have a huge problem down in North Carolina, perfluoroalkane substances, PFAS. PFAS is a major micropollutant, and we need ways of remediating micropollutants and destroying them. So I'll end this with a shout out to my awesome student colleagues at UNC who have helped me start out my independent career, and some nice collaborators here and all around the world, and University of North Carolina for startup funds, which helps support some of the work that you saw, and also the Army Corps of Engineers. Thank you all for your attention. I'd be very happy to take questions. Or comments. Or concerns.
Actually, Stan and Martin were also a little ahead of even the 94 paper, because they were looking at the birth and death statistics for mercury nucleation.
That's right.
So that was
That's
even
right.
a little.
And you know, Fleischmann has a collision of single DNA nucleotides on mercury microelectrodes from 1991 or so.
Yeah, he was more ideas than he had time to explore.
Yeah.
So, but I'm wondering if there isn't also some partial aspect that to a single atom electrodepositing on a bad HER surface. I mean, where is its partial charge? How truly metallic it is? What is happening to the rate as different single platinum atoms get partially charged or discharged?
Yeah, it's a very good question. The short answer is I don't know. But we are changing different substrates from bismuth to carbon to lead to try to see what those differences are. And it's highly dependent on where those atoms come down. There's a pretty big assumption that when an atom comes down on a large surface, it finds the other atoms to build up that cluster as well. And so there's still, this is where I think some correlated types of experiments would be very helpful. So we're working on that, but I don't know yet.
Yeah, this was sort of my question. So do you think that and it sort of relates to what Deborah asked, so do you think that single platinum atom is still ligated by something?
So one thing that we claim in our electrodeposition of nanoparticles is that they are not ligand stabilized. Can I prove that on a single atom? I've no proof.
You have an aqua, there's plenty
Of course,
of water around there, right?
of course.
Water's a
And the
ligand.
double layer around a single platinum atom, I also don't know.
Right.
So there are all these really open questions.
But it needs to be reconciled with the fact that we know from electrocatalysis that a single platinum particle, when it becomes smaller than 1 nanometer, becomes covered by PTO and PTOH.
Depending on the substrate.
Depending on the pH.
Depending on the substrate, too.
Which substrate is platinum?
Now, if it's a platinum atom absorbed onto a different substrate.
No. I'm talking about a platinum particle.
On
there
top
is
of,
a size effect.
There is, but with Zamborini's work, you see a deviation from what Plieth and Henglein predicted, and we wonder if that could be because of substrate stabilization.
Just platinum without
A
being
platinum
attached
particle.
to anything, yes.
Correct.
Becomes covered by oxide. It becomes non-noble after 1 nanometer size. And it's a paradigm since Fils-Ross works on electrocatalysis that's why you lose catalytic activity if you are smaller than 1 nanometer in electrocatalysis of oxygen reduction reaction.
And this is a nanoparticle on what surface?
Non-supported or supported on carbon?
Non-supported?
Yeah,
And supported. It behaves exactly the same.
very similar. On carbon. This is the only relevant support. So this is a brilliant work. It just needs to be reconciled on two sides.
Absolutely.
On one side with the heterogeneous catalysis and the size effects that are very well established for oxygen reduction reaction and the lack of size effects for hydrogen evolution reaction. And on the other end,
Well, we do see a size effect too, but you're saying that folks really, because when they're making these nanoparticles, they're quite polydisperse.
that's
right.
That's a whole other discussion. They could be very
Well, there
monodispersed.
are all of these questions though, right?
Yes.
And I agree, it's going to take all these discussions.
Yeah, but that is why Andy Gehrit was asking you about ligation effect and the water presence, water as a ligand. It's like a native oxide. Platinum is not always noble. If it was mercury, you will be totally right. Platinum becomes non-noble below certain size. It covers with native oxide, and that's been a paradigm of understanding of its reactivity.
Jeff, a very nice talk.
Thank you.
This reminds me, the capability of doing a single or two atom electrode, essentially, opens up a possibility to put one here, and then put one nanometer away, and then build an array and read out, right, spatially, a membrane, a catalyst, surface, whatever you have. But how do you do actually the readout? Because your microelectrodes, your ultra microelectrodes, your super ultra microelectrodes are still going to be macroscopic objects compared to the size of your single atom or your cluster.
Are
of
you
two.
asking how we image it? Reactivity is not a problem. Is
So
it?
just if you want to build an array, and you want to read out individually at position X, Y, that set of particles, right, or that platinum particle.
And so if you have a
atom.
droplet that comes down and you control the number of atoms by the volume of the droplet
Yeah, but
that
you want
pops
to have
off,
this now
say.
space by 1 nanometer or 2 nanometers. You've got 1 million platinum atoms, each separated by 1 or 2 nanometers, and then another million that way, and you build an array that way. How do you read out each one individually? This is like what people
Scanning
are trying to do with
electrochemical cell microscopy.
and it takes time. How do you do it simultaneously at video frame rates, etc.?
Well, you have an array of microelectrodes and you go from one microelectrode to the other.
Those are very, very large, right? They're much larger than the spacing.
Right, but are you worried about diffusion layer overlap from these atoms?
Not just being able to pin down the information from one location and read that out separately from what happens at the next particle over 1 nanometer away.
Yeah, it's a really big challenge, and the thing I would say SCCCM could start answering that if you had different size clusters on an electrode surface, but it'd be very difficult to do. You're absolutely right.
Yeah, but I think that's where it's going, so
Okay.
it's really exciting. Cool. Thanks.
Thank you.